Welcome to the second lecture on the series on sequences of functions. In the last lecture, we defined what is meant by pointwise convergence, and we also analyzed a few examples a little more carefully. If F1 converges to F and epsilon is given, okay, we found that the sequence of real numbers F1 of x must converge to f of x. So this sequence depends upon x. Therefore, if you give me an epsilon, the capital N will depend upon epsilon as well as this particular sequence, which in turn depends on x. Therefore, my capital N will depend upon epsilon and n in general. Okay, we looked at some examples, tried to see what happened there. Okay, based on that information, now we are ready to go into the definition of uniform convergence of functions. Okay, stay tuned, we will get started. Okay, so let me recall what is our definition. We have a set x, just a set, okay, non-empty set. Fn is a sequence of functions from x to r. Then we said F1 converges to F pointwise on x. What was the definition? The definition was for every x in capital X, the sequence F1 of x converges to Fx. This in turn, again we can rewrite it in terms of epsilon. Okay, when do I say F1 of x converges to Fx? If you give me an epsilon positive, there exists a capital N. Notice this N is going to depend upon epsilon as well as x, right? So that for every k greater than or equal to n, mod fk of x minus f of x should be less than epsilon. 1, 2, 3, 4. Look at this definition. Yeah, this is the definition of pointwise convergence. Okay, now what does the uniform convergence is going to matter? It says you give me an epsilon, there is an n which depends only on epsilon, so that for every k greater than or equal to n and for every x in capital X, mod fk of x minus fx should be less than epsilon. That is, my n is not going to depend upon x. Okay, so I say Fn, this is my notation, this is not a standard notation, on x. So whenever you say uniform, you should specify the set. F1 converges to F uniformly on x. Okay, we say F1 converges to F uniformly on x. Okay, if what happens, if for every epsilon greater than 0 there exists a capital N, a natural number, so that for every k greater than or equal to n and for every x in capital X, what should happen? Mod fk of x minus f of x should be less than epsilon. Do you see that? First, let us go slow. Okay, if you are not seeing my way of writing the quantifiers, you may be slightly uncomfortable. Let us do that. What does this say? For every x in capital X, Fn x converges to Fx. Then this is the sequence of real numbers. You know how to write the definition. That's it, right? But I want to write now uniform convergence. What does it mean? You give me an epsilon, I can find an n. So that for every greater than or equal to n, mod fk of x minus fx is less than epsilon. Usually in textbooks, they will write it at the end, the x. Okay, don't bother, I will see. We will write it. How will I write this? If for any epsilon positive, there exists, I'm writing the same thing, there exists a natural number n, so that for any k greater than or equal to n and for any x, for all x in capital X, we have mod fk of x minus f of x is less than epsilon. Okay, I'm writing this inverse. Okay, but usually in textbook what they will do is this, they will write like this for every k, and then they will write for all x in capital X. Okay, they will split this particular quantifier, the universal quantifier for all, at the end. But it's always nice to write it all the quantifiers in the beginning of the sentence in the proper order. That's what we have done. Okay, and also notice that something very interesting in pointwise convergence, where does the quantifier for all x in X comes? It comes at the front, whereas in the case of uniform convergence, for all x in capital X comes at the most interior. You understand that? So this is the first quantifier, second quantifier, third quantifier, and fourth quantifier. Okay, now this is the first quantifier here, and second quantifier, third quantifier, fourth quantifier. You see that? Okay, it's the innermost now. Okay, but it does not matter. You can also write for all x in X for every k greater than or equal to n, but I write it so that it's it will be more dramatic. Okay, in the pointwise convergence, for all x in capital X comes at the front, whereas in the uniform convergence it comes at the end. Okay, okay. Just don't mug up the definition, try to learn this. So what does this mean? Again, let's go back. Okay, suppose I want to say f1 converge to f pointwise on x. What should I do? Okay, as I keep saying, analysis means you have to estimate something or the other. Here what it says is I have to estimate f1 of x minus f of x. Okay, give me x, fix any x in this, I have to estimate this. Okay, so this estimate may depend upon your x and whatever, but when I want to say f1 converges to f uniformly on x, then what should I do is I should estimate f1 of x minus fx, but this estimate should be independent of x. This is the crucial idea. Okay, just keep this vague idea in mind. As you look through examples, work through examples, you will become more comfortable. Okay, so please go through, pause, review, and proceed. Okay, don't mug up the definition. Try to argue, break it into small parts, analyze what it means. Even if you are not thoroughly convinced, don't worry. Okay, slowly you will see your conviction level increases. Okay, okay, let me just make sure it's a recording. Yeah, right. Okay, good. Are you happy? Now let's look at our earlier examples. Okay, I don't know whether this was the first example. We define fn from R to R to be the simplest case, fn of x equal to 1 by n. Then we found, okay, even for uniform convergence, if the limit is not given, what you have to do, okay, maybe I will do that first. Yeah, first, suppose f1 converges to f uniformly on x. Does it imply f1 converges to f pointwise on x? Sure, it does. Why? Because to prove this, what should I do? Give me an epsilon positive, fix any x in capital X, give me an epsilon positive, I have to find an n, right? But uniform convergence already gives me this n, so that whatever k you gave me, a k of x minus f of x is less than epsilon for every k greater than or equal to n. This is true for every x, therefore in particular for the x you had given me. Suppose you gave me a, this said for every x in capital X, this is true. In particular, x equal to a, this is true. F k of a minus f of a is less than epsilon. So what do you find? If fn converges to f uniformly on x, then fn converges to f pointwise on x. Is that clear? Make sure that you understand. It's all similar to any uniformly continuous function is continuous. Okay, it's similar. It's exactly the same argument, right? Then next, okay, now suppose fn converges to f pointwise. Can it also converge to G pointwise? That is, f g are again functions from x to r, and f1s are functions from x to r, and suppose f1 converges to f pointwise, f1 converges to G pointwise on x. Then what do you think we would like to claim? See, these things are never usually discussed in textbooks, right? You would like to claim f equal to G. The proof is again easy. To show f equal to G, what does it mean? This is if and only if for every x in capital X, the value of the function fx should be equal to the value of the function gx, right? Okay, this is what I have to prove. Okay, right. Now let's look at, now what do I know? For give me any x, fix any x in x, then I know fn of x converges to fx. Similarly, I also know fn of x converges to gx, because f1 converges to f pointwise, f1 converges to G pointwise. Therefore, fn of x converges to this sequence. This, remember, this is a sequence of real numbers. If you want, fix an a, because okay, you understand? So this sequence of numbers converge to fa as well as to ga. By the uniqueness of the limit, I know fa equal to ga, and this is true for every a. That means the function f equal to g. Do you understand this? Sure. Now this gives an idea. Suppose I want to prove fn of x to r, okay, is uniformly convergent on x. Okay, now notice that I never gave you what is the limit function f, right? I simply want you to prove fn converges uniformly on x without even telling you what is the limit f. Then what do you think you should do? Remember, if this is true, then we just now saw fn converges uniformly on x, then fn must converge pointwise on x. You understand that? This implies fn converges pointwise, right? This means fn of x must converge to a number. Okay, call it the number as f of x in R. You follow that? So how will I find the limit function now? It just suggests okay, if I want to say fn converges to f uniformly, fn converges to, so not f, fn converges uniformly on x, I have to find the limit function. The trick is, look at fn of x and show that it converges to some real number, call that real number f of x. You understand that? Therefore I have a function f from x to r now. What is f of x? It is nothing other than limit of fn of x. Yeah, right. So I got a function. Then next I will show fn converges to f uniformly. Is that clear? See, these are the small things, okay, you will need later, but all of a sudden in the proof people will just rush through these things. You may not appreciate. So that's why I am making small observations in the beginning. Are you happy now? Okay. Okay, right. Now let's go back to our example 1. So our fn of x was 1 by n for every x in R, right? Now I want to say fn converges to f something uniformly on R, right? So just now I said, what do I do? If you want to prove this, then it should converge pointwise. What is the limit fn of x? It is 0. Therefore I define fx to be 0 for all x in R. Then what do? I have to show fn converge to 0 uniformly on x. To show this converge uniformly on to 0 on x, this x is R. What should I do? I already told you, I have to estimate fn of x minus f of x uniformly. Find an estimate. Okay, find a uniform estimate, whatever it may mean. That is, the estimate should not depend upon x. But what is fn of x? That is 1 by n. What is f of x? It is 0. Therefore what is the answer? 1 by n. You understand? Now this is an estimate. It's actually equal to, therefore it's less than or equal to. You understand that? Okay, this estimate is independent of x. Therefore if you give me an epsilon, okay, by Archimedean property there is a natural number n such that 1 upon n will be less than epsilon. Yeah, therefore if k is greater than or equal to n, then fk of x minus f of x equal to 1 by k, which will be less than or equal to 1 by n, which is less than epsilon. And this is true for all x in capital X. Therefore I have shown fn converges f uniformly. Okay, pause, review, proceed. Yeah, okay. Now let's look at a second example where if again fn's are from R to R and my fn of x was x by n and f was 0 for all x, right? Now let's look at a picture. I do not know that I have drawn a picture. I hope let me see whether I have drawn a picture. No. No. See, when I want something, I don't get it quickly. Okay, it's all right. Okay, let me go back. Right, now let's look at this picture. Let me assume 0 to infinity. Okay, so that I do not see, this is f1, this will be f2. f2 should be actually half of this, but let me know, this will be fn. You understand that? Yeah. Now what we already have seen, okay, this is not uniformly convergent on all of 0 infinity. How did you prove that? The idea is we try to estimate. What is that I have to estimate? f1 of x minus f of x, that is mod x by n. Okay, here x could be a real, also any real number, but anyway. Okay, this I want this to be less than epsilon, but then there is a problem. Mod x should be less than n times epsilon, or n should be greater than epsilon by mod x if x is not equal to 0. You understand that? Therefore this n seem to depend upon x. Okay, so this gives an idea to us, so that the sequence may not be uniformly convergent, but that's not a proof. You understand that? That's not a proof. So to prove this kind of thing is exactly the same way we proved non-uniformly continuous. That is, assume it is uniformly continuous, arrive at a contradiction. Similarly here, what we will assume is, we will assume that is uniformly convergent, then we arrive at a contradiction. Do you get the idea? Yeah, because this kind of, because I try to estimate, I may be incompetent, I may not be able to look at the correct estimate, so I may simply say it's not uniformly convergent. For example, as I said earlier, suppose my x lies only from 0 to r, let us say, then also you will see my n must be greater than epsilon by r, etc. But then remember, if my x is confined only between 0 and r, then I have a better estimate. Mod x by n will be less than r by n, then this is independent of r by n, and this estimate is independent of x. Therefore if I make sure this is less than epsilon, I am through. That means epsilon must be, sorry, n must be greater than r by epsilon. Now this is independent of x. Do you understand that? So I may be incompetent, I may not have noticed my x is less than or equal to r. You understand? So I will look at only this and then say, or there may be some other ingenious way of getting a better estimate. So what all we have to say is, no genius can prove that. Yeah, assume a genius says I have found an n, then I will arrive at a contradiction. Are you following? Yeah, if you had followed my lectures on uniform continuity, you will understand this kind of logic. Okay, right? Now let us look at it. What does it say? Suppose, okay, suppose f1 converges to 0 uniformly on R even 0 infinity. Okay, right. That means if you give me something like epsilon, let us say equal to 1, yeah, or let epsilon equal to half, right? You will see why. I will come to that in a minute. Okay, it could be anything epsilon, but I'm just saying epsilon equal to okay, right? There is an n, so that what happens? Mod f k of x for k greater than equal to n should be less than epsilon, and this should be true for all x in R 0 infinity. You follow that? In particular, this is less than half. In particular, for k equal to n also it must be true. That is, fn of x for all x in greater than equal to 0 should be less than half. But what is fn of x? That is x by n, and x is positive, therefore x by n must be less than half, right? So this must be true for all x, therefore let me take x equal to 2n. Even I can take x equal to n itself. Then what do I get? 2n by n should be less than half. That is, 2 must be less than half. That's a contradiction. Do you understand the proof? Yeah? Pause, review, proceed. Okay. Before I go further, I would like to explain a very geometric way of looking at uniform convergence. Okay, I will work with only something to x to be an interval in R, so that the picture will be easier. Okay, suppose okay, x is some subset of R, let us say AB. Okay, and I have a sequence f1 to R, right? Therefore I can draw the graph. Okay, suppose f1 converges to f uniformly on x. Okay, and let us assume this is the graph. Okay, the picture doesn't look nice. I would like to draw a much better picture. Let me see whether there is a way of doing it. Draw like triangle. No, I have to use only stroke recognizer. Okay, so let me write an easy one then. Okay, this is my graph. Okay, this is my A, perhaps this is my B. Yeah, now if you give me an epsilon positive, okay, what we do, you draw, see this is my fx, right? So this will be fx plus epsilon, this will be fx minus epsilon, right, over x. Do you understand that? So at each point you draw like this. And my picture may not look very good, but okay, I am sure that all of you understand what I want to draw. So this should be like the parallel thing. Okay, the distance between them is epsilon. Here epsilon, 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 so on. And at this point epsilon, epsilon. You understand that? So like this. Okay, this is the graph of f. This is f minus epsilon. Sorry, f plus epsilon. This is f minus epsilon. You follow that? Yeah. Now what, when I say f1 converges to f uniformly on the interval AB, what does that mean is, okay, for k, for this epsilon there is an n, right? So that for every k greater than or equal to n, mod fk of x minus f of x should be less than epsilon. That means my fk of x, where does it lie? It lies from fx minus epsilon to fx plus epsilon. Do you understand that? Yeah. So this is your fx. Let's look at this. So this is your fx. Okay. So this is my fx minus epsilon. This is fx plus epsilon. Therefore, for k greater than or equal to n, fk of x should lie in this somewhere here, and this should happen for each and every x in the interval AB. That means, can you guess what it is? It says for k greater than or equal to n, Okay, the graph should be some, okay, should lie within this. It may be like anything, but it should lie here. Are you following? And another, and for another k, the graph may look like this. Like that. The graph should be, think of this. So you have two horizontal bands, and this is your original f, and graph should lie within this. This is not a graph, okay? I'm sorry, okay, there cannot be cross section, okay? This is okay. Any graph should be like this. It should lie here. Are you following? Please pause, review, proceed. So let us draw graphs of thing. Okay. Now look at this kind of picture, right? Now let us try to draw a graph. Okay, suppose my epsilon is equal to 1, then I can try to draw the graph y equal to 1. You understand this? Let me make this graph, and this will be y equal to -1. Okay, now do you see what is happening? What do I want? After certain stage, the graph of all these my fn's should lie within this band. But you can see as you go towards infinity, that cannot happen. Are you following? Yeah, please pay attention. Okay, that's what we showed. Okay, the picture showed like this. Okay, this is it, and this is my y equal to x by n, and I took something like 1 here, right? And this is at n, and if I have 2n, that's going to be here. Yeah, so it will not lie within this. Okay, this is my y equal to 1, y equal to -1. So the graph should lie within this. After certain stage, everything should lie. That doesn't happen. Okay, please understand. Okay, now let's go to the next example. So the third example you have seen already is fn or functions. We even assumes open interval 0 1 to r. I will tell you why. Even though I looked at closed interval 0 1, I want to look at fn of x equal to x power n, and then we know fn converges to 0 pointwise. I want to know that it's uniform convergence. Okay, this is all right. I want to know this one. And you may recall we already proved in the last lecture the convergence is not uniform, even though we did not use the word uniform convergence at that time. Yes, yeah, but to quickly recall the proof, let us go through this. Yeah, if you want, let me, it may be a good idea to look at no, not this. Oh, I'm sorry, I'm just searching for it. Please bear with me. I had drawn a lot of pictures, so I would like you to look at that. Yeah, now this is the picture of f of x equal to x, f2 of x equal to x squared, x cubed, x power n, x power 10, and so on. This is x power 20, the last one. Now do you see something very interesting? Right, now all of them converge pointwise. Therefore if I put something like epsilon equal to something, let us say this is 0.2, that is 1/5. If I draw this, you can see that as n is very large, you follow that? Yeah, first what do you observe from this picture? See, you should this is what people don't try to learn, how to draw pictures, understand, infer something. One has to improve one's observation power. Look at that. Do you see that? See, if x power n, if n is very large, you remember that, you know that x power n for 0 less than or equal to x less than 1 goes to 0, right? If n is very large, you can see therefore x power n will be very, very close to 0. That's why you can see when n is 20, it goes almost like 0 up to 0.7. Here you can see up to 0.6, this up to 0. You see that? So it's like that, a lazy person. When it reaches 1, all of a sudden it remembers it has to climb up very fast. It has to reach. It's like a lazy person who has to attend a class at 9 o'clock till 8:50. He is lying on the bed. Then he recognizes, oh, time. So he runs to the class. Brushes his teeth, changes his clothes, and runs. Still lazier person will be, he will wait up to 8:55. Then all of a sudden within 5 minutes he will get reach the class, assuming they reach the class on time. So it reaches 1 on time. Do you see that? So if I put something like y equal to epsilon here, can you see this picture what I'm drawing? Yeah, y equal to epsilon here, what happens? You can see, however large I take, there are parts of the graph which are above that, and when does it happen? At points x which are very near to 1. Are you following me? Please pay attention. These are the kind of thing exploring, investigating is never done. We are experimenting. Please learn to do this. Math is science. Science means you have to learn to observe, experiment, explore, tinker around. That's what we are doing. Sure, right? So come back. So what you have done is we have shown this not uniformly. How did we do that? We said let epsilon equal to half. If it can uniformly convergent, there is an n. So that what happens for all k greater than or equal to n, x power n, that is fn of x minus f of 0, which is x power n. Since x is positive, it's just x power n. That should be less than epsilon. In particular, x power capital N should be less than epsilon, x power k. Yeah, that is half, right? Now what does it mean? That means x must be less than 1 by 2 to the power 1 by n. I have 0, and remember 2 is greater than 1, therefore 2 to the power 1 by n will be greater than 1, therefore 1 upon 2 to the power 1 by n will be less than 1, and it's already positive, therefore it will lie here somewhere. Call this point as 0, right? And also remember, you may remember your limits theorem. If a is positive, a power 1 by n goes to 1, therefore when n is very large, 2 to the power 1 by n will be very close to 1. Do you understand? Therefore my x will be very close to 1. Yeah, but I take a midpoint of this fellow, that will be strictly between 1 by 2 to the power 1 upon 2 to the power 1 by n and 1, and at that point, for that point it will be greater, because this x must be less than. You follow what I am saying? So if this were true, then I concluded x must be this. But if I take this point, call it y, this point y also lies between 0 and 1, and y is greater than 1 upon 2 to the power 1 by n. Yeah, but what did we assume? This must be true for all x in cap 0, 1. So in particular for this y also it must be true, but that's wrong. Are you following? Therefore this convergence is not uniform, where it's not uniform on the open interval 0 1. Yes, pause, review, proceed. Now let's have a small break with the technical result. Okay, so now X is any set and Fn converges to F. Okay, Fn F or F are functions from X to R. Right. Now suppose A is a subset of X, non-empty of course. Right. If Fn converges to F uniformly on X, what does it imply about its convergence? Remember, then Fn will also converge to F on A, because for all X in capital X, Fn X converges to Fx. Therefore, for X in A also this is true. Therefore, Fn converges to F pointwise on A. What I am asking now, whether Fn converges to F uniformly on A. Of course it is true. Why? If you give an epsilon, there is an n, so that for all k greater than equal to n, what do I have? And for all x in x, I have fk of x minus fx is less than epsilon. So for the same n, I have the same thing. You give me an epsilon, take the same n, take the same k. Now yeah, restrict x in a, then also this result is true. Therefore Fn converges to F uniformly on x. It implies Fn converges uniformly to F on any proper set, any subset A of X. Is that clear? But what we want is a contrapositive. Okay, please pay attention. This is a logic. These are the things, so people don't take time to learn. So in particular, suppose Fn does not converge. So Fn, F are functions from X to R. A is a subset of X. What I know is Fn does not converge to F uniformly on A. Then I claim Fn does not converge uniformly on X to F. Is that clear? Why? Again, prove by contradiction. Suppose Fn converges to F uniformly on X. Just now we proved in that case Fn converges to F uniformly on A. But hypothesis says Fn does not converge to F uniformly on A. Do you follow that? This is just logic. Now come back to this. Now use it in the last example. So what did we show? Now let's look at the function Fn from closed interval 0 1 to R, and it converges to the function f of x, which is 0 less than equal to x less than 1 and equal to 1 if x equal to 1. Right? Then Fn converges to F pointwise on 0 1. I want to know whether it converges to F uniformly on 0 1. What do you think the answer is? No. Why? If Fn converges to F uniformly on the closed interval 0 1, that should imply Fn converges to F uniformly on the open interval 0 1. But that's not true. Just now we saw. You understood that? Yes? Very good. Okay. So let us see whether there is any yeah. Let's look at one more example before I stop. We will come back to this example. No, let's do one more example. This is, remember we did that Fn from R to R and Fn of x equal to sin nx by n. And then we saw Fn converges to 0 pointwise on R. Okay, in the last lecture. Is it uniform? Is the convergence uniform? What is that I have to estimate? I have to find uniform estimate for this, but that is mod sin nx by n, but that's less than equal to 1 by n. So this estimate is independent of x, right? Therefore now you know how to prove, right? The convergence is uniform. Okay, right. So please go through all these examples. In the next lecture we will continue with a set of 3 examples, okay, and they are done in my book. We will also look at these pictures, graphs of the functions. See, you saw fn of x equal to x power n on the interval 0 1, closed interval 0 1. Okay, the function is well behaved except at 1, x equal to 1 at the end point, right? That's a kind of troublemaking point. Otherwise everywhere it's 0. You understand? So one of the tricks in mathematics is, again, actually in real life, whenever there is a troublesome person, what do you do? Somehow you try to control him. If necessary, you even eliminate him. Yeah. We will try to see how to do that. Okay. And what are the consequences? What does it teach us about uniform convergence in the next lecture? Stay tuned. Okay.